My name is Anthony, and I'm presenting our work on a long horizon planning framework for manipulating rigid point cloud objects. Let's consider a task where a bimanual robot must move an object between two stable configurations on the table. Assume the robot is provided with a set of primitive manipulation skills, along with a high-level sequence of the skills that should be used to complete the task. The system must then determine continuous parameter values, which influence how the skills at each step are executed, so that the robot can move the object to the goal. The long horizon nature of the task already presents some difficulties. However, we also assume that the 3D model of the manipulated object is not known, which creates many additional challenges for current approaches from task and motion planning. Our goal is to overcome these difficulties and enable both generalization to unknown objects and long-term planning. We propose a framework for planning manipulation sequences that solve such long horizon tasks when we are not provided with a 3D model of the object. Our framework operates directly with an object point cloud and plans in the abstract space of object subgoals rather than low-level actions. However, planning in the space of subgoals is challenging, because in general it's critical to produce subgoals that are reachable, and we must also still determine the robot actions that can enable reaching them. Let's first consider this problem of predicting low-level actions that can reach object subgoals. If we restrict ourselves to manipulating rigid objects, then all subgoals can be expressed as a relative rigid transformation of the object. Furthermore, if we assume that the robot makes and maintains a sticking contact with the object, where there's no relative motion between the end effector and the object after contact has been made, then the subgoal can be reached by moving the end effector by the same relative transformation representing the object subgoal. As a consequence, just knowing the initial contact location and the desired rigid body transformation provides sufficient information for formulating a low-level controller that can manipulate the object to the subgoal. In this work, we leverage a set of primitive manipulation skills recently proposed by Hogan et al. That serve as such low-level controllers. These skills operate by taking an initial contact configuration and a desired relative transformation as parameters to compute a corresponding robot motion. However, they were originally designed to only work with cuboidal objects and with known 3D object models. In our work, we generalize the capabilities of these skills to work directly with point clouds and more general classes of object geometries, so they can be integrated within our framework. Even though these skills alleviate some of the difficulties with reaching subgoals, it is possible that some subgoals cannot be reached due to constraints imposed by the robot's workspace, the environment, or the behavior of the skills. Additionally, an initial contact configuration may not be compatible with a particular skill or subgoal if it fails to satisfy our sticking assumption or leads to a collision between the robot and the environment. Typically, one might design samplers using heuristics and prior knowledge about the object to restrict the search space toward feasible subgoals and compatible contacts. However, this approach limits the ability to manipulate novel objects. In recent years, learning-based approaches have achieved generalization to novel objects by mapping sensory observations directly to robot actions. Similarly, to generalize to novel objects, we train neural networks in a self-supervised fashion to directly predict skill parameters from an object point cloud. To collect data for training these networks, we use a self-supervised procedure where the robot chooses pairs of subgoals and contact locations on the object and verifies if a particular contact enables the robot to achieve the subgoal. Using the successful combinations of contacts and subgoals as training data, a neural network is then trained for each skill to map an object point cloud to a distribution over subgoals and contact locations. Because we train only using successful executions, the network learns to predict subgoals that the robot is likely to be able to reach and corresponding contacts that are likely to enable reaching these predicted subgoals. This helps us solve the challenge of planning in the space of feasible subgoals directly from point cloud data. Once we've trained these models for each skill, we then integrate them to operate as samplers into a sampling-based planning algorithm to enable multi-step reasoning directly using the point cloud. Our multi-step planning results show that our framework enables long horizon planning for a variety of planned skeletons with unseen cuboidal objects, and that our learned samplers enable more efficient planning than a baseline sampler that utilizes carefully designed heuristics. We also show that our framework can plan to manipulate objects onto different placement surfaces. Here we show a 5-step plan found by our framework, where the robot places an object onto a shelf. Our qualitative results also show that our learned samplers, which are trained only on cuboids, can generalize beyond cuboids to novel classes of objects. And finally, that our framework can be used to manipulate objects in the real world. Overall, by leveraging our assumptions of rigid objects and sticking contact, and learning to sample feasible subgoals and contacts directly using point clouds, our framework combines the best of hierarchical planning with learning-based approaches to manipulation. On one hand, we generalize planning methods to operate directly with a perceptual object representation, while on the other hand, we are able to plan over long horizons, which remains challenging for end-to-end learning-based systems. For more information on our learning techniques, novel subgoal representation, and planning algorithm, please see our paper. Thank you.